Thank you, Joe, for the introduction. My presentation is about lithium-ion battery pack design for electric vehicles using GT-AutoLion. The problem that we are going to address in this presentation is lithium-ion battery pack design for electric vehicles. And the solution that we propose is multi-physics simulation and multi-criteria optimization. Regarding battery systems modeling, on one side of the spectrum, we have battery cell electrochemical thermal modeling at the component level. And on the other side, we have battery pack electrical modeling at the system level. Of course, we can have a battery pack thermal modeling, but the main focus in this study is about battery pack electrical modeling. And now multi-physics modeling or simulation falls somewhere in between. It means that there is an exchange of information between battery cell model and battery pack model, and we will iteratively design the battery cell and battery pack. In other words, we are taking into account interactions between battery cell and battery pack model in realistic working scenarios. And now let us elaborate a little bit more about how this so-called multi-physics simulation and multi-criteria optimization framework works. At the first stage, we have model development and parameter identification. In our previous study, we developed a calibration optimization methodology for modeling large traction lithium-ion battery packs, and the fully calibrated and validated model will be used here in this study to design lithium-ion battery packs. At the second stage, we have cell design optimization, where we employ GT-AutoLion to model lithium-ion battery cells using the electrochemical thermally coupled approach. The parameters that here we use for the purpose of cell design optimization are electrode thicknesses and porosities. And our objectives at the cell level are specific energy of the cells and maximum cell temperature. At the third stage, the performance of the optimally designed cells will be evaluated at the pack level. And the evaluation criteria here are battery pack energy density, maximum temperature, temperature in homogeneity within the battery pack, and battery pack state of charge. The integration of these two steps will lead to the so-called multi-physics simulation and multi-criteria optimization framework. And eventually, the information will be used for systematic analysis and to provide cell design guidelines. And now, what are the key assumptions that we consider in our simulations? At the cell level, the optimizations are performed at 1.5 C discharge current. 4 cell design cases are considered, because here we are doing multi-objective optimization using weighted sum approach. Depending on the importance that we give to the objective functions, we have defined 4 design cases, and it is important hereafter to remember that as we move from design case A to design case D, the importance of specific energy decreases while the importance of maximum cell temperature increases. The baseline case here corresponds to a commercially available cylindrical cell. At the pack level, the battery pack electrical topology, or in other words, the current imbalances inside the battery pack, is considered. And optimally designed cells at the previous stage are evaluated separately under battery pack working operation. The discharge currents of 1.5 C and C per 2 are considered in our evaluations. And the battery pack cutoff voltage and temperature